So 20 to 30 minutes, let's see how many slides I succeed to go through. So thank you very much for inviting us and coordinating the workshop. And since we have 2 days, I see this as a 3-step presentation, so I'll give you a little bit of an overview of KTH and some of the projects we have running now. And then after lunch, I'm going to go a little bit more in depth into the research that we are doing, and then tomorrow whole day there will be students from both here and then KTH giving detailed presentations about their research. So just to give you a little bit of an idea about KTH, so it has been established back in 1827 and is the Swedish largest technical university. So you see the numbers here, and we usually proudly say that 1/3 of students and faculty are female, and KTH is working very hard on trying to get an even number there, although I think it's going to be very, very difficult. So KTH is actually organized of 10 schools or 10 faculties, so computer science, electrical engineering, architecture, chemistry, and so on. So I'm representing the computer science, so it's one of the faculties or one of the schools. And you get also the numbers here is about 350 employees, and 1/3 of that are actually PhD students. And most of these students are on daily basis sitting at the university doing research together with the senior staff, together with the faculty. Some of them, but the number is very low, I would say 10 to 15% are industrial PhD students, although most of them, even if they are employed by industry, also sit on daily basis at the university. Now, KTH is, for those that would like to visit, placed very centrally in Stockholm and very easy to reach. But it's also distributed over several different campuses, and our school is actually located at 3 different sites. And I think that this is very natural, partially because computer science faculty work very closely to industry. So we are very close to Ericsson, ABB, Scania, and so on. So part of the computer science school is at the areas where the industry is actually situated. And then part of the school is also working very closely to the so-called SciLife lab. I don't know if you know about the human protein atlas research and so on. This is something that has been invested in very much in Sweden during the past 10 years. And lots of the computer science faculty is also working very closely then to applications that have to do with SciLife. That's why 3 sites. Very shortly about funding, I'm not going to go into details, but just to give you a little bit of an idea. So we get governmental support to do basic education. So that would be maybe 25%, 28% of the funding comes from there. And then we also have governmental grants, money that comes directly to support the research staff. And they also pay, of course, for educating PhD students. Everything else comes then from the funding that the faculty applies for, almost 50% of that, from research councils, again, governmental authorities and so on, and of course, as it has been mentioned also, the EU framework programs that are financing very large grants. Now, given that KTH has done 10 faculties, 10 schools, computer science, electrical engineering, mathematics, and so on, we also have so-called umbrella organizations that are working and integrating research over several disciplines. So Center for Autonomous Systems that I'm heading is such an umbrella organization that integrates then electrical engineering, computer science, mathematics optimization theories, but it's also then providing links to industry. And this is very important because when it comes to robotics, as Frank has already said, it's very interdisciplinary research. I mean, if you really want to drag it, it can be everything from neuroscience, basically, then to human-robot interaction, and then everything in between, mechanical engineering, electrical engineering, computer science, and so on. So I think that this is also a challenge and has been a challenge for the field, finding good ways of how to actually integrate that research. So if I'm taking myself, I have undergraduate education in mechanical engineering. I got my PhD in computer science. So I think it's very important also to build faculties and exchange students and have the possibility of having students getting maybe PhD in the area which they don't have their basic education from. So organizing research in this way, how we did it with Center for Autonomous Systems, is, I think, a very good way to do that. Partially also because some of the research questions that we are posing today can also affect and be published in several different fields, but then try to avoid reinvention as much as possible, because we realize today that many of the machine learning algorithms partially can be applied, for example, in automatic control, but we also need to learn a lot about what automatic control has been doing historically in order to understand whether machine learning is an appropriate tool for solving some of the problems. So I think that that's important. One of the things that we have been working very hard with, and this is also open KTH internationally, are different types of master's programs. So the two most popular master's programs at KTH are machine learning and systems control and robotics. This is where we get international students. All courses are given in English, and master theses are also written in English. And this is how we also recruit international PhD students. So my lab, for example, is very international. We have students both from Europe, Asia, somewhat less from US for apparent reasons. If you're educated in US, most likely you want to stay in US. But I think that this is one good way of finding internationally good students and recruiting them and have them stay also in Sweden after they get their PhD, hopefully. This one. So I wanted to tell you a little bit about research that we are doing in the next coming 15 minutes, and then more details in the afternoon and tomorrow. So, Frank has been talking about object grasping and manipulation, and that has been my area of research for the, I would say, past 20 years. In the beginning, when I started to address that field, it was very much about, let's say, industrial automation, looking into how we can use old Puma robots and KUKA robots, industrial robots interacting with the environment. So if I'm to say a little bit about the trends and the things that have changed in that particular area during the 20 years, I would say it has to do with the symbiosis of being able to equip robots with better sensors and integrate, so doing sensor fusion for object grasping and manipulation. So, back in the beginnings of doing this, we did lots of, we used cameras solely to do object pose estimation, for example, try to understand scenes where the objects are and so on. We did this with several cameras because we didn't have 3D cameras and so on. But if I'm to look into what we are seeing now, it's then integrating vision, force torque feedback, haptic feedback, and so on, and trying to do also this in real time. It's still a big challenge, and I would say that one of the biggest challenges are also the hands, as Frank has said. There is very little off-the-shelf advanced hardware that we can buy that to some that can even remotely, mimic the dexterity of human hands. I think that the DLR Justin robot is fantastic, but it's fantastic partially because of the upper body motion, because of the arms. And if you looked into the hands, they are still big and bulky. Yeah, they have 5 fingers, but they still don't have anything in terms of mimicking the human skin feedback. Either for the purpose of understanding, the forces and the torques that are being applied when interacting with objects, but also understanding other properties of objects, such as, for example, the texture, so the type of material, or, for example, the temperature and so on, something that we humans are very good in doing. So we continue to do this research. Luckily, it's still kind of like a very vivid area of research, and will continue to be that, especially if we want to also have hands with high dexterity and of cheap cost. 3D printing does help, but it does not solve all the problems, especially when it comes to sensing. And the collaborations that we had and some of the impact that we made during the past 20 years is partially to the prosthesis design, because, well, we build hands in robotics, but people in prosthetics industry have also been doing this for quite some time. So trying to understand how to give back the functionality to a human that maybe lost a hand in an accident, but not only that, potentially integrating it with the human nervous system, but also adding the dexterity. So although the prosthetic hands today look very anthropomorphic, so they have 5 hands and the right color and so on, most of them still have a single degree of freedom, and many of them still mechanically controlled, so you need to press a certain button to open or close the hand, and they don't almost have any sensing that can feed back to the human anything about the temperature or the type of the material the human is interacting with. So most of these systems are still, let's say, relying on an intact personal, well, the human decision making, so to speak, that the human knows what he or she is interacting with, and the mechanics is still very simple. So here we collaborated during a 5-7 year period with a prosthetics producer called Otobok. So we looked into how we can understand which degrees of freedom of the human hand are the most used ones, the most interesting ones, the most important ones. And in order to be able to do that, we need to look into human hands in daily interaction with objects. So if we want to do that, understand how we humans use our hands without putting any gloves on the hands, we need to be able to extract human hand data from regular videos. So having a human wearing a camera, observing his or her hands in daily interaction with objects. So we use that with different types of machine learning algorithms, for example, to understand whether this motion or that motion or any other motion of the hand is something that is most common, and use that then to provide suggestions of how better prosthetics, more functional prosthetics could look like. One of the things we did not expect, having all this data of how humans use their hands and how also hands interact, what it impacted also was teleoperation or gaming industry, right? Because now we are building this game setups where we want humans to use their natural motion and that is being observed by cameras and interact with things in the virtual world. Now, we are using then the data that has actually been generated for this research to provide better tracking algorithms, better reconstruction algorithms of natural human motion in video. Partially is interesting then for the teleoperation and gaming industry, but something that I also think is going to be very, very important for the future industrial setup is learning by demonstration. So having all those workers that Frank has shown, somehow teaching robots in the future how to do things. And I completely agreed with Frank what he said. Things are, some of those activities that we have seen are impossible to explain by words. And if it's impossible to explain by words how to do, so you take this wire here and you put it there and then you drag it through this opening. I mean, how does a robot really understand that? And sometimes it's actually impossible even to write a computer program that follows instructions that are verbally extremely difficult or impossible to convey. So what I think when it comes to learning by demonstration, understanding visual sequences together with what is being spoken or said, and together with some understanding of what is physically possible, so simulation. So integrating those three is going to be extremely important for the future. So that's why I put learning by demonstration into the last slide. Now, what we sometimes forget is also that, well, how we humans and how perceive the world around us and how robots do that. You know, we forget that we don't measure the same things, or that we don't measure the environment or represent the environment in the same way. So still bridging this gap of what we humans understand and what robots understand, I would say it's still an open problem in robotics. So lots of research that we do at the center is also focusing on bridging that gap, trying to understand how to represent what the robot measures in such a way so that it can be naturally conveyed to human, even if they don't measure the things in the right way, but also going one step forward. And this is using then the things that robots can do and that humans can do, such as, for example, measuring just the distance, right? Because we humans cannot do that if we are not using a special sensor or something like that to do that. Basically use a robot as something that helps human or adds, I forgot the English word now, it's with E, well, it doesn't matter. It extends basically human cognitive abilities. So a robot can be seen as an extra tool. So it's not instead of a human, but in many tasks it will be help, an extra help to the human, such as a tool to provide human with the information that human is not able to cognitively solve himself or herself. Another example of a project that we have been involved in, and this research also continues, I think that sometimes it's also important, apart from solving, you know, as you said, Frank, the industrial tasks, problems that we have right at our doorstep, think a little bit visionary. So how are things going to be in 10 or 15 years, and where are robots going to learn from? Who is going to generate and label potentially all the data that robots need? Labeling, yeah, we can talk about that. We can talk about differences between the supervised and unsupervised learning and robots learning things that humans cannot learn and so on. I completely agree that in the future that's also going to be the case. But we're going to have a pretty long, I would say, period of time where robots are forced to use all the data sources that humans have built for themselves. Okay, so that's also something that we'll look at. So the idea for this project here would, okay, how would a human learn or use the available data out there to prepare a meal that he or she has never prepared before? So that was kind of like the guiding light. What do we do? How do we think? So you invited somebody for a dinner and you want to prepare something that you never prepared before. You first look for a recipe, right? You either go to a book or you just Google the recipe. So you find the recipe of the meal you want to prepare, and you will probably get then a recipe that first gives you a list of ingredients that you need in order to prepare that meal. And then you have a textual description of how to put those ingredients together, so what to do. And both humans and robots are good in understanding text, right? So robots can do that. They can understand all the ingredients that are needed. They can take the list from a recipe and send it to any web-based food store or something like that. And a robot as well as a human can have a set of groceries basically get delivered to the door. That's a solved problem today. Whether you have a drone delivering it or a human delivering, that's another issue, but that's doable. Now, the second problem is understanding then how to put together those ingredients, right? And something that we humans are excellent at, and robots are still very, very bad in that, is how to go from text to controlling your body. So understanding what it means to crack an egg, flip a pancake, That comes very natural to us, but it's still not very natural to robots. So going from text to action. Now, in this particular project, we had an idea, okay, why just not try to understand it visually? Because this is exactly what humans would do. If you don't know how to crack an egg or flip a pancake, what you will do, you will maybe search for a YouTube video. So look into another person or a professional chef, right, doing that particular activity, and you will try to then somehow learn through demonstration. So achieve the same result, maybe not through completely the same type of body motion, but you at least will understand what the result of the thing is. And in many cases, you will both listen and look. So that was the idea in this project. So why just not look into the YouTube sequences and have a robot try to achieve the same result? I would say that no matter, that we have been doing AI for 60, 70 years now, developing robots and so on, doing that, going from human body to robot body is still a big challenge. Maybe deep learning will solve that, maybe not. I can't say. I haven't seen any yet provable or good examples of that. So have a robot just observing a human cracking an egg and doing it itself. That's still a very big challenge. And it's a big challenge because from a video sequence, you can't really understand the type of force or a torque or the feedback that the human is actually using to execute a certain task. So again, doing the multi-sensor fusion and low-level control together with high-level decision-making, it's still a big challenge. A project like this will continue, and I think that in one way or another, this is also a representative kind of problem that many big labs, robot labs in the world are addressing. All the problems from low-level sensory control to high-level machine learning and planning. Another project is Trader project is finishing up this year. And it's not so very much for the purpose of this search and rescue application I wanted to take it up. But it's because in most of the projects we always try to involve as much as possible end users. So if we work with Ottobock and try to understand how to design the next generation of prosthetic hands, we work with the patients. We want to understand what patients need in their daily life. In the Trader project, we wanted to understand how prepared the firefighters actually are for using the very advanced technology. What is the type of human-robot interface they need in order to be able to control drones or mobile robots or anything in that direction? And human-robot interaction is, for us, not, I would say, a key area where we usually go and publish our papers and so on, but that only says about the complexity. Yeah, we can define or develop a very advanced type of robots, but then the end users, the firefighters in this case, they don't know how to operate them. So I think this is also something that we need to think about from the beginning. Not only think about very advanced technology, but think about who will be training this technology. Can those workers in those factories that Frank has shown in an easy and natural way convey their expertise, their manipulation with objects to robots so that it doesn't require much longer time for them to train the robots than it does for them to actually do the task, because nobody will then invest in the technology. We are also very much thinking about not completely excluding humans from the loop, but trying to marry what's good about humans and what's good about robots, and make and look into applications that still use high-level decision-making from humans, but is maybe or applications that are using robots and deploying robots to areas that are dangerous to humans. So Trader was one project like that. Kentauro is another one, where we, apart from than using a human to teleoperate robots. Also want to try to find ways of how to operate or how to teleoperate back the sensory feedback from the robot directly to the human. Okay, so the loop back. So what we are thinking about, if the robot then has a sense of smell, so that there is olfaction, for example, or the robot has force torque feedback and so on, can interact with different type of soil and so on, that comes back to the operator. So the operator here can basically then have some form of a suit or something like that, and we can operate back, for example, the forces and so on, so that it feels for the human as if the human was touching the soil and interacting with the environment that actually robot is interacting with. Let me just then finish a little bit about how I think that funding also affects very much what we do. Okay, when I took over the center, many industrial partners came to us and say, "Oh, we would like to do a one-year project with you. Could you please solve this problem for us?" I said, "No. I don't want to do one-year projects. I don't want to do two-year projects. I think if we want to really do serious research, because it's important for the academics, and also have a long-term relationship with industry, we need to find a way of how to actually, get married in a way. We need to have relationships that are long-term. The industry needs to realize that research is not something that just can be done overnight. So at KTH, we recently got a 10-year grant, which I think is excellent, that actually comes from private funding, from private family, Wallenberry family. I don't know if some of you know that family, but is a family that established and owns ABB, SIS, Scania, and some other companies. And they said they realized that for all the companies that they have in their portfolio, it's extremely important that they get in touch with research long term. So they established this WAS program, Wallenberry Autonomous Systems project or program, that is a 10-year project. And we got money 2015. In a couple of weeks, they are going to announce something similar that is very focused on AI. So I can't tell you more about that. I'm going to be responsible for that part. So just working with autonomous systems is not enough. They realize that AI in itself, as an area, also needs to get more visibility. So they will invest even more money in that area. But when we sat down and think, okay, what are autonomous systems? Where and how we can integrate different disciplines in order to then build scenarios and test beds and so on that are of interest for industry. And that's not so easy to do because, as I said, for robotics, we talk about, everything from automatic control to AI, like planning, decision-making, and so on. Areas that I would say historically have also been areas that have their own conferences published in different journals and so on. But now when we talk about autonomous systems for the society, it's even bigger, right? And we learned that, for example, everything that we do is about both software and hardware. So we need to also put lots of attention in software development. So when we started to talk to software people, then we realized, oh, that's also a community. So just trying to understand which areas and which communities actually need to come together in order to be able to do this, to do research at this scale. Coordinating everything is not so very easy. But so here you see thematic areas, and the idea is that we work with a kind of like a matrix format. And try then to use the intersections in this matrix to define projects that are very thematic, but that marry areas from different disciplines in order to kind of achieve also new and rather interdisciplinary research results. I think I'm going to stop here. I'm just going to give you a little bit of 3 examples that we work with. area one that we work with are vehicles, robots, and humans. And here we think both about applications that are close to humans, like hospitals, elderly homes, and so on. And at the same time, transportation applications, such as, for example, drones and different types of flying vehicles. When we talk about systems of systems, then we talk about the society. So how can we do multiple or multi-autonomous systems in order to address everything from energy consumption, but not on a single robot, at the level of a town, for example, and how research from, for example, machine learning can be used in order to do a more effective energy consumption, for example. That's one example. And the area 3 is software. And I think that this has been one of the biggest challenges for us, because software people, they are very much focused on software being deployed in different systems, and how one does research in this area is also a little bit different from what we in robotics are maybe used to. How do you verify software? How do you update software? How do you make, let's say, safe software? Or how do you make software that checks software? Okay, benchmarking and everything. So we also here have lots of challenges when it comes to, having researchers from different cultures working together and trying to understand what are the research principles and what are the ways of evaluating research in order to then, of course, publish and so on. Since we will be hearing a little bit about underwater robotics, I'm not going to say very much about that, but just one of the projects that we got last year is a very big maritime research project. It's also a collaboration between several different universities. And here you see a little bit about ideas, trying to make autonomous systems, less and less people, both underwater and on the water. And I think that why I actually put this project up, not so much for all the technical aspects that still need to be solved in terms of the robotics and everything, but because it's a very interdisciplinary project. So one big part of this project are marine biologists. Okay, people that came to us and say, we really want to understand what happens with sea life underwater, and how to build robots, how to build autonomous systems that you can use to deploy both, let's say, very deep in the water and just below the water, in order to understand what is happening with fish, what is happening with flora, and try to understand also how different types of contamination affects the sea life. It's important for Sweden, it's important for Norway, but it's also, I think, important for several of the countries and maybe even for this one. So I'm looking forward to find more kind of collaboration areas that we can continue to talk about. So this was this before lunch, and then a little bit more details about the research after lunch. So thank you so much.